NEC section 300.3 addresses the requirements for running conductors together. Specifically, it mandates that for branch circuits, the neutral conductor must be run with the hot conductors. This requirement is primarily intended to prevent overheating of the conductors and surrounding materials. However, the scenario presented involves isolated programmable logic controller, or PLC, output cards that are supplied with an external 120 volts alternating current, or VAC, power source to wet the contacts. These circuits, as described, do not constitute branch circuits in the traditional sense, which alters their applicability to NEC section 300.3. The key factors that lead to this determination are firstly the nature of the circuits. The circuits are used to switch low wattage solenoids. The solenoids only consume 5 watts of power. This low power consumption translates to a minimal current draw. Secondly, the purpose of NEC section 300.3. The purpose of NEC section 300.3 is to prevent overheating, which becomes a significant concern when conductors carry substantial amounts of current. In high current situations, the magnetic fields generated by the hot and neutral conductors can induce currents in surrounding metallic components if the conductors are not running close proximity. Running the hot and neutral conductors together ensures that the magnetic fields largely cancel each other out, minimizing the risk of induced currents and subsequent heating. Thirdly, the isolation of the circuits. The circuits are isolated from the main electrical system. Isolation reduces the risk of short circuits or other fault conditions causing fires or other hazards. Furthermore, because of the very low current draw of the 5-watt solenoids, the risk of overheating is negligible. Fourthly, the exception to NEC 300.3 requirements. Given the low current draw and the isolated nature of these circuits, they are generally considered exempt from the stringent requirements of NEC section 300.3. This exemption acknowledges that the concerns about overheating and induced currents are significantly reduced when dealing with low-power circuits. It is important to consider the specifics of the design and installation. The fact that the 120 volts alternating current, or VAC, power source is supplied from a distribution panel approximately 100 feet away in a different building and the solenoids are installed in a process line approximately 600 feet from the PLC does not inherently change the applicability of the exemption, provided that the current draw remains low and the circuits are properly isolated. In this particular setup, the hot 120 volts alternating current, or VAC, wire is run to the PLC output card, and the switched power is then routed to the solenoids via multi-conductor cable. The common or return path for the solenoids returns to the source of the power, which is the distribution panel, via a different route than the switched power. This configuration, where there is no common in the cable to the PLC cards or from the PLC to the solenoids, is acceptable given the aforementioned conditions. It is crucial to ensure that all conductors are properly sized to account for voltage drop and other factors. While the circuits may be exempt from NEC section 300.3, it is still necessary to comply with all other applicable codes and standards. This includes ensuring that the conductors are of the appropriate gauge for the current they will carry, that they are properly insulated, and that all connections are made securely. It is worth noting that the interpretation of electrical codes can sometimes vary depending on the local jurisdiction and the specific application. Therefore, it is always advisable to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable requirements. In summary, the circuits in question, which involve isolated PLC output cards that switch low wattage solenoids, are generally exempt from the requirements of NEC section 300.3 due to the low current draw and the isolated nature of the circuits. However, it is essential to comply with all other applicable codes and standards, and to consult with a qualified professional if there are any questions or concerns. To elaborate further, let's delve into the specific reasons why the concerns addressed by NEC section 300.3 are less critical in the described scenario. The primary concern of NEC section 300.3 is to prevent inductive heating. Inductive heating occurs when the magnetic fields generated by alternating current carrying conductors induce currents in nearby metallic objects. If the hot and neutral conductors are separated by a significant distance, the magnetic fields they produce do not effectively cancel each other out. This can lead to a net magnetic field that induces currents in metallic enclosures, conduits, or other conductive materials. These induced currents can then cause the metallic objects to heat up, potentially leading to insulation damage, fire hazards, or other problems. However, when the hot and neutral conductors are run close together, their magnetic fields tend to cancel each other out, reducing the net magnetic field and minimizing the risk of induced currents and heating. In the case of the low wattage solenoid circuits, the amount of current flowing through the conductors is very small. This means that the magnetic fields generated by the conductors are also very weak. Consequently, the risk of inducing significant currents in nearby metallic objects is greatly reduced, even if the hot and neutral conductors are not run in close proximity. Furthermore, the fact that the circuits are isolated from the rest of the electrical system provides an additional layer of safety. Isolation helps to prevent fault currents from flowing through the solenoid circuits in the event of a short circuit or other electrical problem. This reduces the risk of overheating and other hazards. It is important to note that the exemption from NEC section 300.3 does not mean that other wiring requirements can be ignored. It is still necessary to ensure that the conductors are properly sized for the current they will carry, that they are adequately insulated, and that all connections are made securely. Additionally, it is important to comply with any other applicable codes and standards, such as those related to grounding, overcurrent protection, and wiring methods. In addition to the inductive heating concerns, NEC section 300.3 also addresses the issue of voltage drop. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. In general, voltage drop is more of a concern when dealing with long conductors or high current loads. In the case of the solenoid circuits, the conductors are relatively long, extending 600 feet from the PLC to the solenoids. However, because the current draw is very low, the voltage drop is likely to be minimal. Nevertheless, it is important to calculate the voltage drop to ensure that it is within acceptable limits. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance, where current is the current flowing through the conductor, and resistance is the resistance of the conductor. The resistance of the conductor depends on its length, cross-sectional area, and material. Once the voltage drop has been calculated, it can be compared to the allowable voltage drop specified in the electrical code. The allowable voltage drop is typically expressed as a percentage of the nominal voltage. If the calculated voltage drop exceeds the allowable voltage drop, it may be necessary to increase the size of the conductors to reduce the resistance. In addition to voltage drop, it is also important to consider the ampacity of the conductors. Ampacity refers to the maximum amount of current that a conductor can safely carry without overheating. The ampacity of a conductor depends on its size, insulation type, and ambient temperature. The ampacity of a conductor is specified in the electrical code. It is important to select conductors with an ampacity that is sufficient to carry the expected current load. If the ampacity of the conductors is too low, the conductors may overheat, leading to insulation damage, fire hazards, or other problems. In the case of the solenoid circuits, the current draw is very low, so the ampacity requirements are not likely to be a major concern. However, it is still important to verify that the conductors have sufficient ampacity for the expected load. Finally, it is important to consider the grounding requirements for the solenoid circuits. Grounding refers to the connection of electrical equipment to the earth. Grounding helps to protect against electric shock and to prevent the buildup of static electricity. The grounding requirements for electrical equipment are specified in the electrical code. In general, all electrical equipment must be properly grounded. The grounding conductor should be sized according to the electrical code. The grounding conductor should be connected to a grounding electrode, such as a ground rod or a metal water pipe. In the case of the solenoid circuits, it is important to ensure that the solenoids are properly grounded. This can be accomplished by connecting a grounding conductor to the metal enclosure of the solenoids. The grounding conductor should be connected to a grounding electrode, such as a ground rod or a metal water pipe. In summary, the solenoid circuits are generally exempt from the requirements of NEC section 300.3 due to the low current draw and the isolated nature of the circuits. However, it is still important to comply with all other applicable codes and standards, such as those related to voltage drop, ampacity, and grounding. Furthermore, it is advisable to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable requirements. To provide a more comprehensive understanding, let's address some common misconceptions and potential pitfalls related to NEC section 300.3 and low voltage circuits. One common misconception is that NEC section 300.3 applies only to branch circuits. While it is true that the wording of NEC section 300.3 specifically mentions branch circuits, the underlying principles of the section are applicable to other types of circuits as well. The primary goal of NEC section 300.3 is to prevent inductive heating and voltage drop, which are concerns that can arise in any alternating current circuit. Therefore, even if a circuit is not technically a branch circuit, it is still important to consider the potential for inductive heating and voltage drop. Another misconception is that low voltage circuits are automatically exempt from NEC section 300.3. While it is true that low voltage circuits generally have lower current draws than high voltage circuits, the potential for inductive heating and voltage drop still exists. Therefore, it is important to carefully evaluate the specific characteristics of the circuit to determine whether the requirements of NEC section 300.3 are applicable. One potential pitfall is failing to properly size the conductors for the solenoid circuits. Even though the current draw is low, it is still important to select conductors that are large enough to carry the expected current load without overheating or experiencing excessive voltage drop. The conductor size should be determined based on the ampacity of the conductor, the length of the conductor, and the allowable voltage drop. Another potential pitfall is failing to properly ground the solenoid circuits. Grounding is essential for safety and helps to prevent electric shock. The grounding conductor should be sized according to the electrical code and should be connected to a grounding electrode, such as a ground rod or a metal water pipe. Another potential pitfall is failing to properly protect the solenoid circuits from overcurrent. Overcurrent protection devices, such as fuses or circuit breakers, are designed to protect electrical circuits from excessive current, which can cause overheating and fire hazards. The overcurrent protection devices should be sized according to the electrical code and should be installed in a readily accessible location. In addition to these potential pitfalls, it is also important to be aware of any local amendments or interpretations of the electrical code. Local jurisdictions may have specific requirements that are more stringent than the National Electrical Code. Therefore, it is important to consult with the local electrical inspector to ensure compliance with all applicable requirements. To further clarify the application of NEC section 300.3 to low wattage solenoid circuits, let's consider some specific examples. Example 1, a 12 volts direct current, or DC, solenoid circuit with a current draw of 1 amp. In this case, the current draw is relatively low, but the voltage is also very low. The low voltage can exacerbate the effects of voltage drop. Therefore, it is important to carefully calculate the voltage drop to ensure that it is within acceptable limits. The conductors should be sized accordingly. Example 2, a 24 volts direct current, or DC, solenoid circuit with a current draw of 2 amps. In this case, the current draw is still relatively low, but it is higher than in the previous example. The conductors should be sized accordingly. Example 3, a 120 volts alternating current, or VAC, solenoid circuit with a current draw of 0.1 amps. In this case, the current draw is very low, and the voltage is relatively high. The risk of inductive heating is minimal. The conductors can be sized accordingly. Example 4, a 240 volts alternating current, or VAC, solenoid circuit with a current draw of 0.5 amps. In this case, the current draw is extremely low and the voltage is relatively high. The risk of inductive heating is negligible. The conductors can be sized accordingly. In each of these examples, it is important to carefully evaluate the specific characteristics of the circuit to determine whether the requirements of NEC section 300.3 are applicable. The conductors should be sized according to the ampacity of the conductor, the length of the conductor, and the allowable voltage drop. The solenoid circuit should be properly grounded and protected from overcurrent. To provide a more practical perspective, let's consider how these principles apply in real-world installations. In industrial settings, low-wattage solenoids are commonly used to control pneumatic valves, hydraulic valves, and other types of actuators. These solenoids are often controlled by PLC, which provide the switching signals to energize and de-energize the solenoids. The wiring for these solenoid circuits can be complex, especially when there are multiple solenoids located over a large area. In these types of installations, it is important to carefully plan the wiring layout to minimize the risk of inductive heating and voltage drop. The conductors should be routed in a way that minimizes the distance between the hot and neutral conductors. The conductors should be supported properly to prevent sagging or damage. The solenoid circuit should be properly grounded and protected from overcurrent. In commercial buildings, low-wattage solenoids are often used to control lighting systems, heating and cooling systems, and other types of building automation systems. These solenoids are typically controlled by building automation controllers, which provide the switching signals to energize and de-energize the solenoids. The wiring for these solenoid circuits is usually less complex than in industrial settings. In residential buildings, low-wattage solenoids are sometimes used to control irrigation systems, security systems, and other types of home automation systems. These solenoids are typically controlled by home automation controllers, which provide the switching signals to energize and de-energize the solenoids. The wiring for these solenoid circuits is usually very simple. No matter what the application, it is important to follow all applicable codes and standards when installing low-wattage solenoid circuits. This will help to ensure that the installation is safe and reliable. In conclusion, the application of NEC section 300.3 to low-wattage solenoid circuits is a complex issue that requires careful consideration of the specific characteristics of the circuit. While these circuits are generally exempt from the strict requirements of NEC section 300.3, it is still important to comply with all other applicable codes and standards. It is always advisable to consult with a qualified electrical engineer or inspector to ensure compliance with all applicable requirements.